Hello everyone, my name is Bach Do from Kyoto University, Japan. It's my pleasure to share with you our recent work on inverse identification of cyclic constitutive law of structural steels using multi-objective Bayesian optimization. I and Professor Ohsaki from Kyoto University co-authored this work. So here what I'm going to talk about today. In structural engineering, we often encounter the forward and inverse problems. In forward problems, we define a set of parameters X, and the goal is to predict the structural responses of interest using a model or a simulation of our structures. And this process we call structural analysis. The inverse problem gives us the structural responses of interest, which obtained from the experiment, and we have to recover an optimal set of parameters for our structures that characterize the response, and we use optimization for this task. In this study, we find the material parameters to model the cyclic behavior of structural steels under cyclic loading like this. And we assume that we have the experimental results from a total of I different cyclic tests of a steel specimen. We find the optimal X by minimizing an error function f of X like this. This represents the difference between the simulated response ds and that's measured experimentally dm. In our previous work, we minimized the error functions for each cyclic test one by one using problem 1, and we also minimize the total values of all the error functions using problem 2. And in this study, we simultaneously minimize the error function here for using a multi-objective optimization formulation in problem 3. So why did we formulate problem 3? We solve here a result from this study to explain our formulation. We identify the parameters for a specimen like this. It's tested under 3 different loading history here. We also define a so-called dataset specific bias, and that means the parameters identified from a specific loading history, for example, SS1, may provide inaccurate prediction of the behavior under other loading histories, for example, SS2 and SS3. We also propose a bias index to indicate the bias level, so that the larger the bias index, the higher the bias level. And we evaluate the bias index for the solutions to the mentioned 3 problems. And obviously here we can see that the solution from problem 3 provides the smallest values of the bias. Solving the mentioned inverse problem require calling the forward problem many times to update the parameters. However, solving the forward problem in this case to computationally is expensive, and also the gradient information of our error functions is difficult to obtain numerically. And also the problem of the bias when we use a single loading history for identification. So in this study, we aim to provide a global optimization framework using Bayesian optimization for solving the identification problem, while we keep in the number of costly simulation costs at a minimum, and also we want to reduce the dataset specific bias. To simulate the cyclic elastoplastic behavior of steels, we use the Cheboche combined hardening model. This model combines an isotropic hardening by this formula with nonlinear kinematic hardening described by this formula. We don't go into detail this model. However, if we use only one backstress component for the nonlinear kinematic hardening and a fixed value of Young modulus and the Poisson ratio, we have a total of 5 parameters to be identified. We move to the Bayesian optimization for solving the identification problem. This is a powerful sequential optimization method for solving optimization problems with costly objective functions like our error function. And it has 2 ingredients, the Gaussian process considered as the surrogates for our error functions, and the acquisition function to guide the optimization intelligently. For example, here we minimize an objective function f. The the top panel here shows the GP model for f constructed from 3 training points. The red solid line here is GP mean, and the 2 dots line here are the GP prediction bounds. We can see them in next slide. The bottom panel here shows the acquisition function for this problem. And to determine the next sampling point that refines the accuracy of our GP, we should maximize the acquisition function, as we can see here. The Gaussian process, or GP, is a probabilistic regression model that provides the prediction of a function and the uncertainty in this prediction. We construct the GP by extending the distribution of numbers to the distribution of functions. This allows us to sample a spectrum of functions like this using a mean function and a covariant function. Similar to finding the parameters for distribution of the numbers, we can fit the spectrum of functions by finding the optimal parameters for the mean function and the covariant function to closely match the given function values in a training data set, which we call the training process. And after training, we can predict the output value for any input vector x star, and this prediction is a Gaussian distribution, and it has 2 sources of information, the mean and the variance. The second ingredient is the acquisition function for our multi-objective identification problem. For example, here we consider 2 this space of objective function, F1 and F2. We have omega here is the current set of 4 solutions, and we also have a fixed reference point here, so that is dominated by all the members of omega. And we define the hypervolume of omega and the reference point as the black area here. And now suppose we have another set of a candidate solution omega 1 and the corresponding hypervolume measure of omega 1. And obviously we can see the hypervolume measure of omega 1 is larger than that of omega. So omega 1 is better than omega. And we can extend this idea to a 3D case or higher dimensional cases. So we want to find the new candidate solutions that improve our hypervolume measures as much as possible. That means we should maximize what we call the hypervolume indicator by this formula, and it's indicated by the green area right here. So that's why the acquisition function now is the hypervolume indicator, and the idea is we improve the hypervolume measure step by step like this. And so here we summarize the identification procedure using Bayesian optimization. We first randomly generate the initial samples of parameters. We construct the GP model for the objective functions. Next, we find the solution among the available candidate solutions using a sorting algorithm. We terminate the identification process and output parameters if one of the 2 stopping criteria here satisfied. Otherwise, we maximize the acquisition function to find the next parameter vector. And we call simulation to evaluate the error functions corresponding to the new parameter vector here. We add the parameter vector and the corresponding error functions to the training data set, and we start a new iteration. So we back to the example we saw before. So here we have the experimental results is the actual stress strain curve in the specimen corresponding to each loading history here. And we have a total of 5 parameters for this problem with the Young modulus we fixed at this value. And the interval for other parameters given in this table. For identification, we use experimental results from every pair of 2 loading histories. So we have 3 identification cases like this. And in each identification case, we generate 3 different training data sets and at the beginning of the BO. So here we have a history of the hypervolume measures for the 3 different Bayesian optimization terms of each iteration case. We can see that even though starting at very different initial values, the hypervolume from each case tend to converge to a unique value when the optimization terminates. And the bottom panel here shows the evolution of the solutions during the first Bayesian optimization terms. We can see that the solution improve after iteration significantly. So here we can see the similarity of the shapes from the solutions obtained from the first, second, and the third identification case. And also for comparison, we perform the standard non-dominated sorting genetic algorithm for 2 times for each identification case, and using the same number of simulation cores. And we can see here that the solution by the Bayesian optimization outperforms though by the corresponding genetic algorithm terms. We use the best compromise solution of parameters from each identification case to predict the stress strain curve from each loading history. And we can see that the parameters can reproduce the stress strain curve for each loading history with a good accuracy. And also we use the parameters to predict the stress strain curve from other loading history SS4, SS5, SS6 right here. And we obtain an acceptable accuracy right here. And finally, here are some conclusions through this study. Thank you very much for listening.